All right. So, hello and welcome everyone. We will today go through the Bitcoin Optech newsletter, number 323, which was published on 4th of October 2024. And this week we will probably cover this news article. The first one that is impending btcd security disclosure. Anton Ponce posted to Delving Bitcoin to announce the planned disclosure on October 10th of a consensus bug affecting the BTCD full node. Using data from a rough survey of active full nodes, Ponce surmises that there are about 36 BTCD nodes that are vulnerable, or the 20 of those nodes are vulnerable to an already disclosed consensus vulnerability. See newsletter number 26. In a reply, BTCD maintainer Olaoluwa Osentokun confirmed the existence of the vulnerability and that it was fixed in BTCD version 0.24.2. Anyone running an older version of BTCD is encouraged to upgrade to the latest release, which was already announced as security critical. So, we have talked about what is a responsible disclosure, right? So whenever there is a bug in any software, it is not generally, it's a principle that you do not announce it in public until and unless the threat that that bug might pose is mitigated, right? So the general principle is you report to the maintainers of that software, or if there is a dedicated team of security experts, then you report it to them. And once it is reported to them, then that team of trained experts work on mitigating the threat posed by that vulnerability. And once they are certain that there is no more threat to that vulnerability being announced in public, that is when they go out and announce it in public. So there is a bug that has been detected in BTCD, which is one of the implementations of Bitcoin. That bug will be released or announced on October of 10th. That is 3 days from now. Okay, so the bug is not yet disclosed. There is a bug that will be announced on October 10th. That is when the maintainers or the developers of that client, along with the people who found out that bug, feel it would be safe. So they are informing us beforehand that hey, we have discovered a bug in BTCD. All right, and if any of you are using BTCD, then upgrade it before October of 10th. After October of 10th, we will announce that bug and that vulnerability in public, and then everybody will be aware of it. And if despite us announcing, you do not upgrade your node till October 10th, then your node is susceptible to a exploitation of that vulnerability. All right. And few weeks ago, another bug in BTCD was also discovered, which 20 nodes were vulnerable to. Okay, and that bug was announced, and that bug was fixed in this version. All right, it was fixed in version 24.2, and later on, when there was no threat of that bug being exploited, or people were given adequate time to upgrade their clients, after that, that bug was announced. Now, the current bug that is being discussed in this newsletter is impending, meaning that is not being announced. Right? They're just telling you, hey, we've discovered a bug. We're giving you time till 10th of October. If you are running a BTCD node, then upgrade it before 10th of November and upgrade to the latest version, after which we will release the vulnerability. So we can't talk about what this vulnerability is because they've not even discussed it, right? So, but what we'll do is we'll talk about a previous vulnerability that they have already disclosed, right? So, a similar vulnerability was discovered a few weeks ago, which was announced in this newsletter. We'll go through that vulnerability, and while doing that, we'll cover BIP 68 and BIP 112 and relative time locks in Bitcoin. Okay. So let us read what this vulnerability was in BTCD that was disclosed some time ago. Cool. Let's read through it first. Disclosure of fixed consensus failure in BTCD. Nicholas Gerber used Delving Bitcoin to announce a consensus failure in older versions of BTCD that he had previously responsibly disclosed. Relative time locks were added to Bitcoin in a soft fork by adding consensus enforced meaning to transaction input sequence numbers. To ensure any pre-signed transactions created before the fork would not be made invalid, the relative time locks only apply to transactions with number 2 and higher, allowing transactions with the original default of version 1 to remain valid with any inputs. Okay. So we have had this field called end sequence in Bitcoin since its inception. Okay. What was the initial concept or the reason of having n sequence, it was to RBF transactions. Okay, so initially it was intended that the n sequence field in a Bitcoin transaction will determine which transaction replaces which. So if I have broadcasted a specific Bitcoin transaction, okay, and I want to replace that transaction with another transaction, I will broadcast a conflicting transaction with a higher sequence number. So now we have two conflicting transactions, okay, two transactions with conflicting inputs. How will it be determined which is the latest one and which is the earliest one and which abrogates which? By the sequence number. So the transaction that has the higher sequence number supersedes the transaction that has the lower sequence number. This was the initial intention behind adding sequence numbers, but this was futile. This did not work. This had a flaw in it. Would anybody like to take a shot at what flaw this had? So a miner sees two transactions, okay, two conflicting transactions, only one of which can enter the miner's mempool, right? Now the miner is expected to choose the one with higher sequence number, but this does not meet rational. What could be the reason? Would anybody like to take a shot? Why did this concept of replacing transactions using sequence number fail and it did not go through? All right, so
I'll
the
just
answer.
take a random
Sure,
guess if that's okay.
sure, it's welcome.
I think it could be because sequence number is not used to calculate the transaction hash. So a man in the middle attack could be possible by somebody changing the sequence number.
No, the sequence number is used to calculate the transaction hash. The sequence number is in the input, and the input is used to calculate the transaction hash.
Okay, okay.
Is it because the sequence number is just arbitrary and you can come up with any numbers? There's no guarantee that they are actually in sequence.
Right, but if you are creating a transaction, it is sequence number serves that purpose, right? So when you are a developer, or even if you are a Bitcoin user who is curating his own transaction, you know that the sequence number has a purpose, right? So if you have created a transaction with a sequence number and you want to replace that transaction, okay, with another transaction, the second transaction, the latter transaction should have a higher sequence number. So that is the intention of that was the intention of having sequence numbers. Yes, it could be arbitrary, but there is a purpose, right? So if you are creating a Bitcoin transaction and you have broadcasted that transaction with a certain sequence number, and then you realize that, hey, I want to replace this transaction for any reason. Maybe you feel the fee is low, you want to bump the fee. What do? You recreate another transaction with a higher fee, and this time with a higher sequence number. So you beforehand know that the sequence number in the transaction is serving a certain purpose.
But I guess this is more of a question then. Can someone else make a different transaction with a higher sequence number, or can I make a higher sequence number transaction with a lower fee?
You absolutely can, and you've partially, maybe implicitly answered the question. Nobody else can. You can, because you need access to the private key to sign the transaction, right? Only you have the private
I
key,
see.
so
Okay.
you can, yeah. But it's
Yeah.
absolutely possible for you to have a higher sequence number and a lower fee, and that is where the catch is.
Right. Because then the miners are not incentivized to accept your higher sequence number.
Exactly. The assumption that the miners will unconditionally give preference to a transaction which has a higher sequence number is erroneous, because the miners will give preference to transactions that pay them the higher fee. So even if the sequence number is low, if it's paying a higher fee, the miner will give preference to the fee and not to the sequence number. And that is why this assumption was erroneous. Okay, so this was the initial use case of sequence numbers. Initially, sequence numbers were in Bitcoin to signify or imply which transaction is the later transaction, which the miners would use as an indication to select the later transaction. But it is erroneous, because miners will select transactions on the basis of which transaction pays them a higher fee. So they won't care about your sequence number. They will choose transactions that pay them more money. All right. So that is why this concept never took off. So it's like a did you know kind of a thing. Okay, it is not a part of this news article, but it's a did you know kind of a thing. So sequence number, the use case or the purpose of sequence numbers have evolved, or n sequence has evolved over a period of time. Actually, it was intended to be used for RBF. Okay, so all transactions that have version number 1, for them sequence number were intended to RBF transactions. So if you want to replace a transaction, you replace it with a higher sequence number. That was initially, as long as we had only version 1 transactions. Then a soft fork happened, and transactions with version number 2 were incorporated, and the use case or the purpose or the functionality of sequence numbers were changed. After that, sequence numbers were used for relative time locks. Okay, so we have two types of time locks in Bitcoin. One is a transaction level time lock, which locks the entire transaction. That is known as n lock time. And then we have this thing known as sequence numbers or end sequence, which locks specific inputs. All right, so it does not lock the entire transaction; it locks specific inputs. Okay, so now we know that sequence number, its use case has evolved over time. If you see a transaction which has version number 1, then in that case the sequence number was intended to be used for RBF. And if you see a transaction with version number 2, then in that case the sequence numbers or the end sequence are used for relative time locks. Okay, so however, in the original Bitcoin software, version numbers are signed integers, meaning negative versions are possible. Okay, so the reference implementation section in BIP68 notes that version 2 and higher. So when up till we had version number 1, okay, back then the version numbers were signed integers, meaning it was also possible for a Bitcoin transaction to have a negative version number. It's still possible, by the way, okay? But the standard transactions in Bitcoin were considered as version 1, okay? But it was absolutely possible for a Bitcoin transaction to have a negative version number, which is even possible today. But the catch is, if you look at BIP68, if you happen to read BIP68, BIP68 mentions that relative time locks are only applicable to transactions that have version number 2 or higher. 2, 3, 4, 5, 8, 10, whatever. Okay. 1 is standard, 2 is standard, and right now, as we speak, even 3 is standard. Other than that, nothing is standard. Okay, they are not standard. They are consensus valid, but they are not standard transactions. Okay, so you can, as a miner, you can grab them out of and put it in your mempool. Okay, they're absolutely valid transactions, consensus valid transactions, but they're not standard transactions. Okay, so if you broadcast a transaction with version number 5 or 6 or 7 or something like that, they will not be considered as standard transactions. Okay, so BIP68 says that all transactions that have a version number 2 or higher, okay, the end sequence in them will be used as a time lock parameter. Okay, now what's important to note is that it says version 2 and higher, which means 3, 4, 5, 6, but it excludes negative numbers, right? -1, -2, -3, they are not higher. Okay, so what it means that negative version numbers are not compatible with relative time locks. So after the soft fork was introduced for time locks, what was done is that initially we had the version numbers were not casted, right? They were signed integers. What is a signed integer? It can be positive, it can be negative. It can have a positive sign, it can have a negative sign. But now, after the soft fork that activated relative time locks, we have time locks that depend on version number. After that, what we started to do is we started to cast the version numbers. Okay, we only started using version numbers as positive. Okay, as positive. So the version number would be taken, and to check for time lock compatibility, it will be converted to a positive value to be casted. All right. So if it's -3, it will be considered as 3. If it's -2, it will be considered as 2. If it's -4, it will be considered as 4. Okay. Uh, I read this again. However, in the original Bitcoin software, version numbers are signed integers. Okay, so up till version 1, we had version numbers are signed integers, meaning negative versions are possible. The reference implementation section of BIP68 notes that version 2 and higher is meant to apply to the version number cast from a signed integer into an unsigned integer. So with this soft fork onwards, the relative time lock soft fork onwards, we started treating version numbers as unsigned integers, meaning they cannot have negative values. They'll be typecasted, especially for BIP68 and BIP112 compatibility checks. Okay. Other than that, they can have negative values, but while checking for relative time locks, they are converted into unsigned integers, ensuring that the rules apply to any transaction that isn't version 0 or version 1. Okay, so if there is a transaction that has version number 0 or version number 1, relative time locks will not be applicable to them. Other than these two, whatever the version number is, -2, -3, -5, -25, 2, 3, 4, 5, 6, whatever it is, they are all time lock compatible. And if they are negative, then they will be casted. They'll be converted from signed to unsigned. So if they're -5, -6, -7, whatever, they'll be converted to positive. Why? Because BIP68 says that the version number should be 2 or higher for the transaction to be time lock compatible. All right. Berger discovered that btcd did not implement this conversion from signed to unsigned integers, so it was possible to construct a transaction with a negative version number, which Bitcoin Core would require to follow the BIP68 rules, but btcd would not. Okay, so here is what the catch is. I'll repeat it again. I can repeat it slowly, and I'd be happy if somebody would want to summarize what the bug was. All right, because the bug is here. It's in these three lines. Gerger discovered that btcd did not implement this conversion from signed to unsigned integers, so it was possible to construct a transaction with a negative version number, which Bitcoin Core would require to follow the BIP68 rules, but btcd would not. All right, what's the catch now? Where's the bug here? Why does this break compatibility between btcd and Bitcoin Core? The bug is in these 2.5 lines.
Because one of them forces conversion of negative numbers into positive numbers, while the other one doesn't. Which means you can have, negative numbers which are lower versions than, I forget, it has to be greater than one or wherever you started.
Right, perfect. Yeah, version 2 and higher. So let's assume that there is a transaction which has a version number -2. Okay, now your Bitcoin Core node will convert it into positive, right? It will convert it from signed integer to unsigned integer. So that -2 for Bitcoin Core will be 2. But BTCD was not doing that. BTCD was not converting version numbers from signed to unsigned integers. So that version number will be -2 for BTCD, and that version number will be +2 for Bitcoin Core, right? Now, what will happen is that for Bitcoin Core, that transaction will have time locks, and for BTCD, that transaction will not have time locks, right? And in that case, Bitcoin Core might relay a block which contains a transaction that has a time lock, and BTCD will reject that block. It will consider that block to be invalid, which will lead to a disruption, a lack of communication between two Bitcoin clients, right? And that is what the entire bug was about. So yeah, well summarized by your name is, your pseudonym is Repeat Sumo. Yeah, well summarized by Repeat Sumo. Okay, let's read further. In that case, one node could reject the transaction and any block that contained it, and the other node could accept it and its block, leading to a chain split, right? So if you're running a BTCD node, your blockchain will not accept that block that Bitcoin Core has already accepted, which obviously will lead to a chain fork, right? Because a chain only keeps on building by referencing the previous block, right? So the Bitcoin Core will keep on building the chain by referencing the previous block. But because BTCD will not accept that block as a valid block, BTCD cannot build on top of it. So there will be a chain split, which is very dangerous. An attacker could use this trick an attacker could use this to trick the operator of a BTCD node or software connected to a BTCD node into accepting invalid bitcoins. The bug was privately disclosed to the BTCD maintainers who fixed it in the recent version 0.24.0. Anyone using BTCD for consensus enforcement is strongly urged to upgrade. Additionally, Chris Stewart replied to the Delving Bitcoin thread with a patch for the same failure in the Bitcoin S library. Authors of any code that might be used to validate BIP68 relative block times are urged to check the code for the same stuff. All right. Summarizing it again, initially, sequence numbers were used for RBF. However, that mechanism was erroneous because the miners will give preference to the transactions that pay them a higher fee and not to transactions that are of high sequence numbers. So later on, the use case or the functionality of sequence numbers were amended with a soft fork. After that soft fork, which activated BIP68 and BIP112, sequence numbers were used to imply time locks, and sequence numbers would only imply time locks for transactions having version number 2 or higher. So if you see a transaction with version number 1, there the end sequence is interpreted as signaling RBF. And if you see a transaction with version number 2 or higher, there the sequence number is interpreting a relative time lock. Okay. Now the issue arises with the fact that BIP68 mentions that version numbers 2 and higher are eligible for time locks, which means that the version number should always be positive. So that is why what we do in Bitcoin Core is that we cast the version numbers, and if the version number is negative, we converted into positive to ensure that all version numbers except 0 and 1 are compatible with time lock. However, BTCD was not doing it. So if somebody creates a Bitcoin transaction with a version number, for example, -2, then Bitcoin Core will consider the transaction to be a valid transaction and apply time lock to it. However, BTCD would consider that to be a negative, will consider that to be an invalid transaction because it does not comply with the rules stipulated in BIP 68, which would lead to a transaction being considered valid by Bitcoin Core but considered invalid by BTCD, which would lead to a block being considered valid by Bitcoin Core and being rejected by BTCD, which eventually would lead to a chain split. All right. And how was it fixed? It was fixed by introducing casting in BTCD as well. It was just a one-line change. I think I have it open. It was just a one-line change. That is it. Okay. So this is BTCD. This is on Bitcoin Core. It is BTCD. All right. It's an implementation. It's a client of Bitcoin. Just like we have Bitcoin Core, we have BTCD, and there are around 60 public nodes, 60 public node runners that are using this implementation as well.
I wanted to ask a question while we were waiting for Faisal to join. So this is about how we repurposed version numbers to do something different, right? I was wondering if. Sorry, go ahead.
No, I'm not the version numbers. We did not repurpose the version numbers. We repurposed sequence and sequence tree.
Oh, maybe I misunderstood then. I thought that earlier version numbers were for, one purpose, and then since that didn't work because, you could have a higher version number with the lower fee, therefore it was repurposed for end sequence and said that after a version number 2, it means something else.
Okay, all right. Let me share my screen. Is my screen visible?
I see it now.
Okay, I will show you a Bitcoin transaction. Okay, so this is how a Bitcoin transaction looks like. I'll show you two things. Okay, now there are two ways, or in fact, there are multiple ways, but there are two primary ways in which you can represent a Bitcoin transaction. This is the hexadecimal output. Okay, this is how a Bitcoin transaction looks in its hexadecimal output. Now there is an RPC command, decode raw transaction. When you use this RPC command, decode a raw transaction, and you pass as an argument the hexadecimal value of a Bitcoin transaction, you get this output. So this output, this is the Bitcoin transaction. Okay, this is a Bitcoin transaction. If a normal person asks you how does the Bitcoin transaction looks like, this is how a Bitcoin transaction looks like. This is the hexadecimal representation of the same Bitcoin transaction. Where is the version number? The version number is this. Okay, so when you convert a Bitcoin transaction into its hexadecimal output, into its hexadecimal equivalent, okay, what it starts with is the version number. Okay, so if I show you this hexadecimal output and I tell you this is a Bitcoin transaction, tell me what version is it? Is it version 1, version 2, version 3? Okay, here you see it's version 2. Okay, now I want to convert it into human readable format, right? Humans can't understand anything from this. If I give you this transaction, you cannot understand anything, right? This is for computers to understand. For humans to understand, we convert it into a format called JSON object. Okay, so you decode it. You decode it so that humans can understand it. This is how it looks when you decode it. Now, when you decode it, you have a field called end sequence, right? You can see end sequence. This end sequence was initially used for RBFing. Okay, so if end sequence was 1, and then I use the same input. I use the same input. Okay, the same input, and I change the end sequence to 2. It means that I want the end sequence number with 2 to be my final transaction. Okay, so I create a transaction, I broadcast it with sequence number 1. Then I decided that no, it's paying a very little fee. Now I need to increase the fee. So I increase the fee, and now what I do, I change the sequence number to 2. So the minus is that okay, these are two competing transactions. One has sequence 1 and one has sequence 2. So I have to choose sequence 2. This is what was the intended purpose. But the condition is that the version number should be 1. Here it's 2. Okay. So initially in the earlier days of Bitcoin, the version number, the standard version number was 0 or 1. Okay, so I hope you understand now the difference between version number and sequence number. Sequence number is here. You'll find sequence number when you decode the transaction and you read it in its JSON equivalent. And version number, it's just like, software have version numbers. Version number 1, 2, 3, you have Android 15, 20, whatever it is. I don't know. You have iOS 16, 17, 18, whatever. So Bitcoin transactions also have version numbers. Like initially 0 and 1 were the standard version numbers. Then we went to 2 and now we have 3. Okay, so if the version number is version number 1, their n sequence will serve the role of RBF, and if the version number is 2 or 2 onwards, 3, 4, 5, whatever, there this field n sequence number will serve the role of time lock. Is it clear?
Thank you. That was very helpful. I was confusing version numbers and sequence numbers. I think my question is still something I would like to understand, which is, so when we change rules like this, do we implement a condition saying that this new interpretation of the rules is valid after a certain block height? Because what if before we made this change, someone had used a higher version number with a different end sequence number, and at that point in time, the transaction was considered valid, and based on this new rule change, it's not. How would that
Yeah,
work?
we do that. We do that. We do that. So if let me see if I can show you without wasting a lot of time. If you go to Bitcoin core and there is this file called chainparams.cpp where you will find consensus rules, and I think we should be able to view. Oh, sorry. Okay, I'll zoom in when I find the right code snippet. You will often find block heights as well. Okay, let me zoom in. You can see. So these are heights basically. When BIP 34 was activated at this height. When was BIP 65 activated at this height? When was BIP 66 activated at this height? When was SegWit activated at this height? Right. So if there is an upgrade that you perform which is dependent on block height, then you will stipulate that block height, and only after that block height will that transaction be eligible for that upgrade. So yes, you do that.
Okay. Thank you.
Right? Yeah. Welcome. Okay, all right. But here, as we can see, the version number is 2. What does the sequence number now mean? The sequence number now means block height. Okay, it means that once this transaction has been mined, at least one block has to be mined on top of it for this transaction to be eligible to be spent, right? Because just now we discussed that transactions that have version number 2 or higher, for them the sequence number serves as a time lock. So if I see a transaction that has version number 2, I know that the n sequence field here is for time locks. And your sequence is 1, which means that if this transaction gets mined in block 100, let's say, you can only spend this transaction after block 101. So you can spend it in block 102. You have to wait for one block after it is mined. Okay, if the sequence is 2, 3, 4, 5, whatever, you have to wait for that many blocks before it can get mined. All right. So this is an example. This is a transaction that I myself created. While creating, this is how we create a transaction. Create raw transaction. Okay. You give the TX ID of the transaction from which you're spending. The vout is the output number and your sequence number 1. So you can create your own transaction. You put the sequence number 1, which means that once this transaction gets mined, you have to wait for one block for it to be eligible to be spent. This is the address of the recipient, and this is the amount of bitcoins that I'm sending. Okay, it's version number 2, your sequence number 1. So once this transaction gets mined, it cannot be spent till at least one block is mined on top of it. All right. So yeah, let's go back to this. This is how we fix it. Initially, we were not typecasting it, right? So initially, we were just checking what the version number is. If it was higher than 2, only then time locks were activated. If it was lower than that, time locks were not activated. But now what we are doing is we are creating the version number. This object is this the transaction object, and this is the version number. Okay, we are using this data type uint, which means unsigned. U here stands for unsigned, and unsigned means it can only be positive. It cannot have a negative sign. All right, so there's just one line of code that was made, I believe, on January 22nd. Okay, on January. So the change was made on January 22nd, and the bug was disclosed, I think, on March. It was disclosed, I'm assuming, in March. Okay, so after this fix was made, an update was released, and people were given 2 to 3 months of time to update, after which this bug was released to public. That's how it generally happens. Okay, all right. Let's just go through BIP 68 briefly. We have like 15 minutes or so. Okay, what are time locks? How do you interpret time locks? Okay, so here, as you can see in the JSON object, the n sequence number is 1, right? This is human readable. Okay, but this is not computer readable. Computer understands only binary. So you have to convert the sequence number into binary, right? The computer will convert the sequence number into binary. I think I have it in my notepad. Okay, so when you convert 1 into hexadecimal, this is how it looks. And when you convert 1 into binary, this is how it looks. Okay, so this is 1 interpreted into a 32-bit field. Your n sequence number is a 32-bit field. So when you convert the decimal number 1 into its binary equivalent of 32-bit, this is how it looks like. Okay, so this is how this number one over here, that humans, you and I can understand this one. This is how we see it, but this is how the computer sees it. This is how the computer sees it. Okay, now the computer will use this format to determine whether the time lock is active or no, whether the time lock is based on blocks or on Unix timestamp. Okay, so you can lock a transaction based on two parameters. You can lock it to a block height that, hey, this transaction will only be spendable after a certain block height, or you can lock it in accordance with the Unix timestamp that, hey, this transaction can only be spent after such and such time has been passed. Okay. So how is that determined? Okay, now the computer will convert your n sequence number into this format. It will use this to determine whether the transaction has a time lock, a relative time lock to it or no. And if it has a time lock, is that time lock interpreted in terms of block height or in terms of Unix timestamp? How does that happen? That is stipulated or defined in BIP68. Okay. So first, what is done, if the bit number, if the bit, this is the 31st bit of the sequence number is set. What do you mean by set? Set means 1. Okay, 0 is unset, set is 1. Then no consensus meaning is applied to the sequence number and can be included in any block under all currently possible circumstances. Okay, so the 31st bit, okay, we just now discussed that the n sequence number is converted into a 32-bit field. Okay, so if you look at this that I show in my notepad, these are 32 bits. Okay, 1 2 3, if you count, there are 32. Okay, so we start from 0. This is 0. Okay, and this last one is 31. So if the first thing that will be done is that the last bit will be looked. Okay, is it set or is it unset? If it's set, it means it's 1. If it's unset, it means it's 0. Okay, so here what is it? It is unset. If it is set, then it means there is no time lock. If it is unset, means there is a time lock. Okay, so the interpreter will convert your n sequence number into a 32-bit binary field. The first thing it'll do is it'll look at the 31st bit. Okay, this last one. It'll see it's 1 or it's 0. If it's 1, it means there's no time lock. If it's 0, it means there's time lock. Okay, so as you can see, I've applied a time lock in this transaction. Okay, I've applied a time lock. So here you can see it's binary equivalent. The final bit is 0, and the BIP says that if the final bit is set, then what does it mean? It means that it can be included in any block, meaning it does not have a time lock to it. But in our case, it's 0, right? Which means it is unset, which means it has a time lock. As you can see, in our case, it's 0, so it has a time lock. What's the next thing it'll do? If bit 31 of the sequence number is not set, then the sequence number is interpreted as an encoded relative time lock. Unset meaning 0, not set meaning 0. So ours is 0, which means it has a time lock. So if the final bit is 1, it does not have a time lock. If the final bit is 0, then it has a time lock. The sequence number encoding is interpreted as follows. Bit 122 determines if the relative time lock, or bit number 22 in fact, determines if the relative time lock is time based or block based. Okay, so I just now mentioned that you can lock a transaction based on the block height or based on the timestamp, Unix epoch timestamp. Okay, so how do we find out that? We look at the 22nd bit. Okay, so we look at the 31st bit to see whether there's a time lock or there is no time lock. If there's no time lock, case closed. If there's a time lock, next thing we do is we check the 22nd bit. Okay, now why is the 22nd bit significant? If the bit is set, meaning if the bit is 1, the relative time lock specifies the time span in units of 512 second granularity. The time span starts from the median time pass of the output's previous block and ends at the MTP of the previous block. If the bit is not set, the relative lock time specifies number of blocks. So if the 22nd bit is set, meaning it's 1, in that case, the lock is in the terms of Unix epoch time. And if it is unset, meaning it is 0, then in that case, it is in a term of block height. Okay, here you see. So if this is 1, it means that the timestamp is in terms of Unix epoch time. And if it is 0, it means that the timestamp is in terms of block. Okay, so here I have specified this in terms of block. How do we know that? We look at its binary equivalent. If we look at the 22nd, this is 31, 30, 29, 28, 27, 26, 25, 24, 23, 22. This is 22. Okay, I don't know if this is visible. I'm trying to zoom in. Okay, so this is 0, right? And this also, let me zoom it. So this is 0, which means there is a time lock on it. This is 0, 22nd byte, which means that the time lock is in terms of what? It is in terms of block. If this was 1, it means it is in terms of height. If it is 0, it means it is in terms of block height. Okay, 1 in terms of timestamp, 0 in terms of block height. And here as well, here if it is 0, then it has a time lock. If it is 1, it does not have a time lock. Okay. And then if it has a time lock, what is the value of that time lock, right? Now we figured out that, okay, fine. The final bit is 0, which means it has a time lock. The 22nd bit is also 0, which means that the time lock is in terms of blocks. But how many blocks? How do you know how many blocks? 1 block, 10 block, 100 blocks? How many blocks do we have to wait before this transaction becomes eligible to spend? Your first 15 bits determine it. Your first 16 bits determine it. Okay, starting from 0. Your first 16 bits determine it. Now let's look at our example. Okay, our n sequence is 1. When we convert it into its binary equivalent, this is it. So the first 15 I'm assuming is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. This. Okay, this. When we convert this, we take this binary, okay, the first 16 bit, and then we convert it into its decimal equivalent, it becomes 1. Okay, so this binary value when converted into decimal is what? 1, right? 1, which means only 1 block. So if the n sequence number is 1, if you convert it into its binary equivalent, this is what it becomes. Okay, you look at the final bit, that is the 31st bit. It is 0, meaning it has a time lock. Then you look at the 22nd bit, it is 0, meaning that the time lock is in terms of blocks. Then you look at the first 15 bits, and it is this. You convert it into its by a decimal equivalent, it is 1. It means that this transaction has a time lock in terms of block, and the block height is 1, meaning after it is mined, you have to wait for 1 block. Okay, so that is how the 68 implements uh, the time lock. So you can take any Bitcoin transaction, go to mempool space, play with it, take any Bitcoin transaction. Okay, you take its transaction ID, then you convert it into its hexadecimal equivalent using your terminal. Then you convert it into its JSON object using this decode raw transaction, or you can just create a random transaction on your own using a rectest node. You look at the sequence number, right? You can add the sequence number here while creating. I've chosen 1. You can choose 10, 20, 100, whatever you want. Okay, and then you get the number here, you convert it into its 32-bit binary equivalent. Then when you convert it into its 32-bit binary equivalent, you look at what the final flag is, whether it's set or unset. Then you look at the 22nd bit, whether it's set or unset. Then you take the value of the first 15 bits, and that is how you determine whether that transaction has a relative time lock or no. If that relative time lock is in terms of blocks or of Unix epoch timestamp, and what exactly is that block height or that Unix epoch timestamp when the transaction becomes eligible to be spent. Okay, so this was just kind of a deep, yeah.
Do we know why they limited it to just 15 bits for the relative block height?
I am assuming that I mean, because this is binary. Okay, so I think this value is sufficient. This value is sufficient. Okay, there is I think there is if the value is less than, I think some 5 million or something like that, I might be wrong with the number. If it's less than that, then it is in timestamp, and if it is greater than that, then it is in block height. So I think this gives you a sufficient value. Okay, so if you said, even if you set all of these bytes 1, it's going to be a huge number. So I think it's an adequate window. It gives you an adequate window which you cannot surpass, at least currently. In the near future, you cannot surpass it. So this gives you
Trying
an
to
adequate
do
height.
the math. 2 raised to 15 is, if I'm not wrong, 32,000. So that's 32,768. So that's actually less than 1 year in terms of relative.
I will have to do the math and get back to you. Okay, that is a valid question. Why was it chosen 15? But I'm pretty sure that it has an adequate window. It has an adequate window. As far as the exact math is concerned, then I will get back to you. I probably, if any of you are interested, you can take it up as whatever your self study or whatever you want to dig deep into it. Okay, and convert it into it. But why exactly 16-bit? I will have to invest some time into look into it. Why exactly did they choose 16-bit? And get back to you. All right. Okay. Moving on. Where do we go from here? Yeah, so that's about it. Okay. So when I did this for the first time, this is covered in Mastering Bitcoin, which is generally the first technical book that you study on Bitcoin. When I did this for the first time in Mastering Bitcoin, I did not understand at all how N sequence is implemented. Did not understand because I come from a non-computer science background. I'm a non-tech guy per se. So I did not understand what binary numbers are. How do you convert a decimal number into hexadecimal and then convert it into binary? And what is a flag? What is set? What is unset? And what is an end sequence number? I it just went over my head. So, but now I understand it. So if any of you are like going through mastering Bitcoin now, it'll all make sense to you, and you can take any random transaction and figure out whether it has a relative time lock or no. Okay, but yeah, we can look into it. I'm not pretty sure that I'll be able to do it myself because of bandwidth constraints. I'll try my best because it's an interesting subject to look up to. Multiplying 2 to the power 9 or equivalent shifting up. I'll look into it if time permits. But yeah, others as well. There are others as well. So maybe
Yeah,
even your
no,
will get time. Yeah.
yeah. I can just research that. I was just curious if you knew. That's fine. Thank you.
Yeah, sure. Research it, and if you come up to an inference before others do, please share it and Discord so others can benefit from it as well. For now, the answer is this is how it is. They chose 15. All right. Moving on. So yeah, that's about BIP 68. Let's go to BIP 112. Okay, how BIP 112 does is that once you've chosen your M sequence number, okay, your script must know whether the transaction is successful to be executed or no, right? How does your script know? Your script execution must fail. The script must fail if you're trying to spend a transaction that is not eligible to be spent, right? How do you do that? A new opcode was introduced known as check sequence verifier. Okay, this is BIP 112. It's called CSV, op CSV or op check sequence verify. Okay, so we have redundant codes in Bitcoin which are known as NOP, which don't do anything, all right? So whenever we need a new opcode, we can use these NOP codes and change their functionality. So NOP code basically means that an opcode which does not have any functionality as such, you can override them just like we have overriding operators in Python and in every programming language, right? Where you can change the functionality of a sign. Like so, plus sign is generally used to add to integers, for instance. But if you can use plus sign, you can create your own custom data types. You can create your own custom implementations. You can use that same plus sign to subtract two integers, right? So we had an opcode. We override its functionality and converted it into an op CSV. What does an op CSV do? Is when you are executing the script, it will check if the stack is empty. If the stack is empty, then the script should fail, right? Because the op CSV needs something to check itself against, right? It needs a sequence number to see whether the sequence number is valid or no, whether the transaction is eligible to be spent or no. So if op sequence doesn't get an argument to operate upon, if the stack is empty, then op CSV will fail. The top item on the stack is less than 0, okay, which means that if it is a negative number, right, block height cannot be negative and time can also be negative. So you cannot lock a transaction to a block height which is negative, neither can you lock a transaction to a timestamp which is negative, right? The block height always has to be positive, it has to be in the future, and the time also has to be negative, it has to be in the future. So if the value on the top of the stack is less than 0, then the script will fail again. The top item on the stack has a disable flag, one unset, okay? And so now it will first check that the 31st bit is unset, meaning it should be 0. That is the first test that it should pass, meaning that this should be set to 0. That is the first test. But just because this is set to 0, it does not necessarily mean that the transaction is eligible to be spent. There are other checks that need to be made, right? The transaction version less than 2, then what do? Then you don't, then the script should fail, right? Because if the transaction version is less than 2, even if the last bit or the 31st bit of the end sequence is unset, meaning it is 0, still we cannot set a relative time lock to it. Why? Because transaction version numbers less than 2, 0 and 1 are not eligible to have a relative time lock, right? So we've already studied that the transaction version number needs to be 2 and higher. So if it's less than 2, they are not eligible to be having a relative time lock applied to that. So they, even if the 31st bit is set to 0, if the version number is 0 or 1, then the transaction is not eligible to be relative to have a relative time lock and the script must fail, meaning OptCSV will fail. The transaction input sequence number disable flag is set. Okay, so if I mean one thing is that you pass an argument to opcsv code, and the other thing is the n sequence number. So even if you pass an argument to opcsv which has the last bit set at 0, but the n sequence number, this n sequence number does not have the last bit set at 0, it means that you've not passed an actual n sequence number to opcsv, and in that case also your script will fail. The relative lock time is not the same, or okay, so if the n sequence number or the argument that you have passed to opcsv is in terms of blocks, but the one that is in the transaction is in the term of Unix epoch timestamp, then the script will fail. Or if the n sequence number in the transaction is in the term of blocks, but the argument that you passed to opcsv is in the time of blocks, there's a mismatch, then again your script will fail. The top stack item is greater than the transaction input sequence number when masked according to BIP68. The top stack item is greater than the transaction input sequence. So there is a sequence number in the transactions input, but the argument that you pass to opcsv is greater than that. Is greater than that. In these four situations, even if the final bit is 0, your opcsv will fail, meaning your script will fail. Okay, so this is BIP 112. So BIP 68 specifies the rules based on which we determine whether a transaction is eligible for time lock or no. Okay, it specifies the rule that we check the final bit to see whether it is time locked or no. Then you check the 22nd bit to see whether it is time locked in terms of blocks or in terms of height. Then you check the first 15 bits to see whether it is what exact is the value in which it is time locked, whether in terms of block height or whether in terms of timestamp. Okay, why 16 bits? We will look into it. All of us will together look into it. I don't think that BIP mentions it. Even if it does, I'm not aware of it. So we'll look into it. All right. So this is what BIP 68 does, and this is why it's significant. So BIP 68 was integral in the soft fork. Okay. So if anybody asks you now what does BIP68 do, you know that BIP68, what does it do? It tells us how to interpret n sequence numbers, and it tells us how to use n sequence numbers to determine whether a transaction has a relative time lock or no. If it has a relative time lock, whether the time lock is in terms of block heights or of Unix epoch timestamp. If if it does have a relative time lock, whether in terms of block height, whether in terms of Unix epoch timestamp, how exactly to interpret and evaluate what that block height is or what that Unix epoch timestamp is. All right. We've also seen an example in the binary form here. And now once you've done that, your script must also know that. Okay, your script must also know that. So how does your script fail or pass depending upon whether your transaction is eligible to be spent or not, right? So let's say there's a transaction that is time locked. Okay, it's time locked for the next 100 blocks, but I'm trying to spend it. When I'm trying to spend it, the script should be able to detect that this transaction is not eligible to be spent for the next 100 blocks, and the script should fail. How does that script check it? The script checks it in accordance with BIP 112. So BIP 112 raised the rule. BIP 112 raised the rule for determining whether the script should execute or no. If the transaction is valid, if the time lock has been expired, then the script will execute successfully. And if the time lock is not yet expired, then the script will fail. How? It is these checks that it performs. It is these checks that it performs. So basically, what we covered in this week's newsletter is the fact that version numbers are used to determine the functionality of n sequence. If the version number is 0 and 1, the n sequence is used to interpret whether was used to interpret whether the transaction is RBF or not. Okay, and if the version number is 2 onwards, then the sequence numbers functionality changes. It is used to interpret time locks. Okay, how do you interpret time locks? Time locks are interpreted based on BIP68. We went through what BIP68 is. It is how a time lock transaction is executed on the script. There is a specific opcode known as Optech sequence verify or opcsv that performs these checks on the script to validate whether a time locked transaction is eligible to be spent or no. Okay, so if I have created a transaction, we also saw a dummy transaction. Okay, if this has n sequence 1, the script will check whether that one block has been passed or no. If that one block has been mined and the transaction is now eligible to be spent, the script will get executed. opcsv will return it true. And if that one block has not been mined, I'm trying to spend a premature transaction, then opcsv will return a false and the script execution will fail. Okay, so yeah, this is what the bug was. That we also looked at the bug. Okay, this is what the bug was, that Bitcoin Core was typecasting it I'm not sure if I can show you if I have that open. If we can see Bitcoin Core as well. If we can see Bitcoin Core version view in, let me see. Was before, yeah, version. In version, let me see where it's defined, where it's declared, sorry. Actually, yeah. Yeah, here you see, right? So you see Bitcoin Core, what does it do now? It casts it into UNT. What is UNT? U here stands for unsigned. Okay. So even if the transaction number is -2, okay, if this N version is -2, what is Bitcoin Core going to do it? Bitcoin Core is going to convert it into a positive value, an unsigned. So even if you pass a negative version number -2, Bitcoin Core will convert it into this data type. Okay, unsigned. It will convert it into 2. Okay, which BTCD was not doing initially. As you can see, BTCD was not typecasting. It was just taking the version number and comparing it. But now even BTCD is casting it, right? As you can see, UNT. This is the fix. So now this has been fixed and that bug has been solved. Now there's one more bug again. That bug they have not disclosed. Because they've not disclosed, we did not discuss it. But I decided let's discuss the previous bug. Next bug they should soon disclose it. They will disclose it in October 10th. I'm assuming in the next newsletter we will have that bug. So maybe we can look into that bug as well. Yeah, that is all I had to share from my end. I will stop sharing the screen now. If there are any questions, anything anybody would like to share, please feel free to go ahead and do so.